नमस्ते अनि स्वागत छ यहाँहरूलाई AFU पडकास्ट रूपान्तरण कृषिका कुराहरूको नयाँ अङ्कमा। वेलकम टु द ब्रान्ड न्यू एपिसोड अफ AFU पडकास्ट रूपान्तरण केही कृषिका कुराहरू। आज हामीहरू हाम्रो यस स्टुडियोमा कुनै पनि अतिथिलाई बोलाएका छैनौँ। हामीहरूले यस पटकको अङ्कलाई यसै साता कृषि तथा वन विज्ञान विश्वविद्यालयमा कृषि सङ्कायले आयोजना गरेको एउटा अन्तर्राष्ट्रिय सम्मेलनको विषयलाई जोडेका छौँ र यसै सन्दर्भमा यही माघको 20, 21, 22 तदनुसार फेब्रुअरी 2, 3 र 4मा इन्टरनेसनल कन्फरेन्स अन एग्रिकल्चर ट्रान्सफर्मेसन फर सस्टेनेबल फुड सिस्टम भन्ने शीर्षकमा यस कृषि तथा वन विज्ञान विश्वविद्यालयमा भएको इन्टरनेसनल कन्फरेन्सको किनोट स्पिकर्सहरू जुन विभिन्न देशहरूबाट विभिन्न विश्वविद्यालयबाट आउनुभएको थियो, ती किनोट प्रेजेन्टेसन्सहरूलाई हामीले समावेश गरेका छौँ। आशा छ स्टेक होल्डर्सहरूलाई, पोलिसी मेकर्सहरूलाई, विद्यार्थीहरूलाई, स्टुडेन्ट्सहरूलाई र साइन्टिफिक कम्युनिटीलाई ती प्रेजेन्टेसन्सहरू युजफुल हुनेछ, इफेक्टिभ हुनेछ र सोही अनुसार हामीले चाहिँ आजको एपिसोड बनाएका छौँ र त्यसलाई हेरेर माया गरिदिनु होला। धन्यवाद।
I would like to start today's keynote presentation session. And to start, first of all, I'd like to introduce our first presenter of the session, Dr. Jane Yang. He is the Emeritus Professor at National Chongqing University, Taiwan, and Visiting Professor at Agriculture at the Forestry University. Also, PhD, MS, and BSc in entomology from National Chongqing University with a background in plant medicine, and he also served as president of the Biological Society of China, Taiwan, and as a scientific advisor for the National Geographic Channel. He has published extensively on insect taxonomy, biodiversity, and bioacoustics, specializing in Orthoptera and Cicadae.
Almost every year I try to come once, but I think the organizing committee invited me to give the talk. So actually today I will share you about if you are outsider, how can you become an inside, right? And actually, I have to also thank the university make me become as go home. Actually, this is partially my home, because yesterday the Dean Arjun said I'm partially Nepali. I'm very happy. Right. Okay, this is sorry. And this is a long story. I don't want to tell you. And if you want to know, and I will stay someday longer. Maybe we can meet in the campus. And I also would like to talk to some other professors about the cooperation between Taiwan and Nepal. But I'm sorry, it's nothing about China, sorry. And here was the story why I'm here, because you have very outstanding alumni. And I also very adore that you have such very successful education from here. It's the IAS is before and AFU now. Your students come abroad and ask me to give some insect taxonomy course here. So I just come, and since it was 10 years, more than 10 years. And today I just follow the topic. Actually, everybody knows outsider like me, and actually here we have one case about everybody maybe the very serious insect pest is a FoA armyworm. Recently it's very serious, but actually FoA armyworm not published by entomologist. It's published by a botanist. And there's so many others, like is a Darwin, but actually he was trying to become as a medicinal doctor, Linus too. But finally he became as a natural history And as we know, the subject today, we have to think about, if I just give the abstract, then you will find the answer in the abstract. Actually, not for propose the strategy for you to do the transformation, but this is a way for you to think about reversely. Do we always think about follow the international or the global issue and make everybody busy, right? But if you thinking and rethinking, you will find the way. So this is the point. And normally we think about the strategy must be very detailed discussion, and maybe we have to think about from the pure science like me, the taxonomy, then becomes we identify the insect pest. Then now you have to join the work. So I think I would like to join to give some contribution, right? Okay, so all because of the agriculture, sometimes we say it's positive or it may be negative. And in this case, we have to think both at a time. We have reformed the nature, because nature is there, but reformed for growing our plant becomes a wood or something. And now we suddenly think, this way will cause some harmful to the environment. Like most soil scientists knows, actually soil looks is the same physically, but the inside actually changed. No matter the underwater level, no matter some chemical retained, no matter you reform the topsoil, the A level is changed. So you cannot expect the soil still has such function, right? So now we think about the transformation, of course, not the abiotic one, right? So we think about the biotic one, the direction. So if we think about the agriculture is 10,000 years before we start, and the people get the agriculture benefit. So we have 3 meals a day. Normally, the human anthropological thinking is the record is we have individual eating, then we have the family eating together. Then we have the symposium. Actually, symposium, this word, means eating and the discussion. So we just have the breakfast, the lunch together, and the discussion. That's symposium, right? But normally we have two meals, because when you are not now we have here we have the 2 meals. I come, and I think why? Because we waiting for the meal. It's by time or by your stomach. You're hungry, right? But actually not. We are trying to have the meal because we need energy. So you working, before you working, you have to feel the energy, right? So it is the world not reverse, because now we faced so many risks. We faced the challenge because we made something wrong before. So should we go to think about, so I have the inner dialogue myself, right? In my brain, I say, okay, everybody knows, anyhow, you have no free lunch, right? You have to pay. And now the payment is our risk and the challenge. And no endless enjoy. After quickly happy, then you get some, overnight drunk, right? Maybe sick. And if you has no vision for the offspring, then you will worry about, recently English young people, they don't want to have the baby because they worry about the environment is not enough for the offspring give a good life. So when you think about this, and then you say, oh, no, then say yes. Yes, what? Right? I think, not possible, but we have to do. That's like face the war. The whole country, you have to go. The West Nine, West Nine is the movie, right? Everybody come, and the university students go to the front here. So transformation is necessary. But how? And every different scientist go the different way, but we go the same goal, the same target. And it is for me, worth to do effort to that. And the global issue, I don't have to repeat again here, because yesterday, so many outstanding speakers, the keynote speaker, and the outside, the poster, I see everybody almost knows what happened outside. Not only sunshine, sunset, but you have to think. Maybe in the morning we come, in the sunshine, but the afternoon, maybe the raining. It comes like a chaos, no regulation. So if someday, maybe you find the sun, the sunshine will be from the west, not from the east to the west, right? Okay, just too much crazy, right? And you think if this is data from the innovation, and you have to check again, not just follow the data. See, this is supposed to be finished to achieve the level, in 2030. But finally, just 2023, they have the flattering of emission is far from, that. That means, you cannot catch up your target, right? And okay, I'm not spending time here because I am not a specialist in this part. But you find the global issue of FAO is there, talk about the net zero emission. So now you have the other mission, not only the agricultural program, but also net zero. Yesterday we have the talk about the animal, but actually the animal, the methane emission is how can you count in the reasonable formulation? Because in Taiwan, we are not very in the animal production. So, people also use the global one, like Netherlands, like New Zealand. Even the poo-poo, yeah, and the air, it cause affect the emission, the GHG. So they think, maybe we have to stop animal industry. But it is not necessary, because this is just small part in the case. But if you say this, and nobody wants to think about okay. Okay. So now I think we have to think about the, you have the new issue coming, right? And this one is the net zero, maybe, you have to edit more manpower, more energy, more budget to do that. But the agricultural one, the food system, and you cannot have more money. So now we use the net zero emission budget to support the food system, right? So actually, international mission, the issue becomes many heads. So you don't know where you go. So we have to set, the transformation as the goal, and then we try to make many ideas together to mobilize, the climate finance to unlock the problem, because this is the paid lunch must be the climate change. So also climate change also comes to peoples because of our past behavior. So now it's transformation necessary. So today we talk about the transformation to support the food in the future. But we have to rethink it again, right? So for me, I would like to join this discussion. But okay, this is, we just skip, everybody knows. From the chaos, the many things to integration must be, meeting, like a conference like this one, to have the brainstorming, right? So this is, at the beginning, I said that if the soil is such situation, and now the animal. So in Taiwan, actually we are island, right? All the agricultural cropping is maybe from outside, and we are not introduced, but maybe they were bred by the people, and then finally becomes the native one. So we always say, how can you get rid of the invasive plant? The first one is rice, the paddy field, because they introduced this one. And the animal and some other food plant, and I mean the fruit and the flower and many things. It's not necessary for the meal, but they do need for your nutrition. So you added more, and then now we think about the taste. We are enjoying our, olfactory, our sense. So this comes to the value is becomes not very the orthodox, the direct way to think. Okay, let's go back to think from the environment, right? So the soils decline. That's the problem. We also have to think about this. Okay, this is just a bridge for us to think what kind of the service, I mean, the result from the nature to help us. Originally, is for food, only eating, and now it depends on the organism. I mean, the nature. We say the natural history structure. So compared to this one, we think about mostly we need the support from the nature is materials, right? You have to have the wood. You have to have some wood for the construction for house. You need the gasoline for traffic. All the material one, and some regulation. You cannot see they're working, but they are there. And you also think about some supporting system, you know, and then now people think about the history is so long, you know, that you look back the nature history because of the people, so make this life become as meaningful, and you become as very abundant of your life. So this is I make this graph to show you different support from the nature is actually from agriculture too, right? But this is we say the ecosystem service, and agriculture is actually is a ecosystem. Okay, this is more detailed, and so now I find the ecosystem. I find the lot when I almost think in the marine sea, right? In the sea. So I find this is my point. So I said taxonomy become as the porting system, you know, for the sustainable, right? And I know it's so taxonomy and biodiversity. Actually, biodiversity is a mega science to merge everybody comes. So if we think about the taxonomy to the life science, then you can think about the global issue. From global change, it was just 30, 40 years ago. And now the sustainability, as people think about not only the food supply and also your life, the culture. So now comes to the insect. So many insects. Not every people knows how to do the identification. So most of the people actually you do the recognition, not the really the recognition, you know, and not really identify. How many species you can recognize, right? Maybe you look different because this is selected by the taxonomist to put there. If you put the similar together, then you can make difference. Okay, okay, and this is a situation. The number every day change because when taxonomists publish a new species, then the number change. So we cannot compare the number to say how about the biodiversity, right? How about the diversity? I mean, the species number is abundant, and you know, even new order happened. But actually, this is only the new species. But the new species representative one order is 100 years happened once, right? Not every day happened. Okay, and okay, we can skip. We need only very simple, you know, facility. Then you can see the normal applied scientist you don't think about, right? And we need no microscope before. This is electronic microscope. And then taxonomists do recognition, I mean the identification, different from the applied and more applied scientists is something like this. This is a locust migratoria from the Asia. You know, this is you see this is 3 species, and the top one without the mark, the hindwing without the mark. You know, that you can easily to find. Oh, that's different. And actually, the locust migratoria is the top one, and the others is a local species from Taiwan. Maybe you have the different, but if sometimes you use the key, use a pictorial key to identify your species, say no mark is a locust migratoria in your country, maybe wrong because you have other species maybe similar. So you have to find the second character for identify to make it different. This is because we have the taxonomic system, then you can identify, follow the system. So we always say taxonomy is working from the bottom to the top to establish the system. But the identification is based on the system to identify, the exactly species. Okay, so that's different. It was different species. That's slide, right? Then this is this is the same species but different form. So if you investigate, you survey the species outside, I don't think you can very easy to find the difference, right? Okay, so again, I think we need people to aware. If you want to join this work, these tasks, and you have to try to go the perfect way to purchase the result. So at least that you have the collection. So I think the museum collection is very important. But for other animal, maybe they just need the corner to put the specimen. But to insect is too tedious, right? Okay, so actually classification, identification, recognition. Taxonomy is for the purpose. So taxonomy is in this time, we find the way to join the transformation. If we think about the insect species, right? Even you don't have to know the species name. You don't have to identify yourself because you just find and tell the taxonomist where you collect, right? And what time you collect, when. Then we know the season and we know the places, the habitat. Then maybe we can give the whole picture, the higher scaling up, then give you the whole picture. And you make the key, yourself, not the taxonomist make the key for everybody. It's so reverse, right? I give the thinking is different. And if you say the last, the bottom one, the right, actually this is a new species and also new genus happened in Taiwan. I published, and 6 months later, our Japanese colleagues published in Amami Island, right? Right? It's the second species, only 2, right? And he just find the 2 individuals. Fortunately, he has 1 male, so it's a taxonomy done. But the identification is very different, difficult, right? It's all similar. Something like this, we need very different. Like this is my study, so I just skip quickly, right? It's something about so to the agro-ecosystem is just like the same. You need to investigate not only one pest or the nature enemy. You have many, you don't know their relationship, the altruism, right? And again, actually, we think about the organic farm, organic agriculture. Most of the people ask me, how can you find the insect living together, but without injury, damage to our crop, right? I say, if they are not phytofocus, they don't eat your crop. But if they are decomposer, they're waiting for your fruit drop. And if they are a borer, they're waiting for the fruit, dried out. Then the seed come in. That's all, right? And if you have the borer to the trunk, the stem, then it's die out, right? The tree. So something like this, you said, what is organic agriculture? They say, actually, in the field, all the organic, but you have to take action to get rid of the problem happen. But now we find one case, then we statistically data show you how to do the large area, the scale. Then you spend, a lot of money because for the maybe 1% risk, right? Okay, so then we say, if we say actually simply we think about it, because we are talking about agriculture is human life supporting. So from biodiversity issue, it's always, from the agriculture, because agriculture make, the product through the production level. But now, organic, or we say the sustainability, means the production not only from the agriculture. So that means agriculture, we need some, natural, natural field, support nature, the world. So in this way, you also have to think about which one is positive to your support, the life, and which one is negative. So we only get rid of the negative one, because the negative one is not always happen. So you also have to do some investigation, then monitoring, then making the formulation or the strategy. Then this is the way we can join. And in between the work, we have to think about, maybe we don't always think, the insect, they are eating each other, right? So we think, actually, sorry. We say the last, we say mutualism, altruism, and the neutralism. Actually, even before, we think about the aphid and the ladybug, right? They are help each other, right? And the ant and the aphid, they help each other. But actually, in the pineapple, the ant actually they are as a nurturing the mini bug and become as a pest, right? So now we don't say that they are natural enemy or the predator or the parasite, but we said they are doing cooperation, because in the community they stay. They live in the same places, and they have a different niche. So, okay, this is the way. I just give this part because of eating, the recipe change our agricultural system. Okay, this is too far for this day. This is in Taiwan, and the Bangladesh is very close to you, right? Singular. Okay. In terms of yesterday, we talked about the bean. Some study about the different bean. You have the intercropping system, but actually this is a corn. Corn and the bean has a different the root system. So maybe this is a nitrogen matter is the bean, right? And the corn becomes a protection line. It's very easy for the bean crops, something like that, right? Okay, I'm not to stay here, but we have to go back in the soil as an example, right? Because soil is the best. Most people say, soil then becomes we said the overuse, and even in the agricultural system, sometimes we have to fill up the soil from outside to reform. And at the beginning, I said reform costs now our burden, our risk, right? So if you keep the soil, you have to think about the soil is available or not. That means it's is adopt for the agriculture or not, right? So if we say if you talk about the soil experimental, you are not to see the growing, the crop growing first or not, but you have to think about the totally biomass, because finally their remainder also comes to the soil and it becomes a nutrition to the soil, right? The cycling is not by human, but the natural cycling. Okay, I'll skip. Okay, done. So the study of this, we think about the cropping remainder, the agricultural remainder in the field. But we also think about, many organisms depends on that kind of a situation to sustain their life. I think Professor John is also soil mesofauna, very familiar, so he knows. So we use this Paris Huno to separate the insect out. Okay, sorry, the time is over, right? Okay, sorry, quickly. So we invent many ways to collect the insect and describe not only the species, not only the individual, but we have to think about so many things. How can you make this become meaningful? Okay, quickly, right? And you have the weapon, you don't have the bullet, right? So you need a bullet. So we have the bullet, but you don't have the planning to when is the time to shoot, right? And this is the way, this is a working procedure, it's a SOP. Then we find, this is a composition of the insect in, from the primary consumer, second consumer, and the decomposer, parasite, and whatever. So we make this, in the percentage comparison. But actually, we also simply use the pi. This is temporary. You cannot compare the percentage with the percentage, right? And we make this, actually, this tower, food tower, actually, you need many different organisms, including plant and other animals. But only the insect we can make is this one. This is for the forest ecosystem. We spend 10 years to do with the LTER and find the forest, Guandaoxi, is like this one, right? Okay. And we also find that, totally all the agricultural pests, the cropping pest changed because of our cropping system changed. So, the insect changed. Sorry, I think we have, it's the English one. Okay, you find that that's the red one is the major insect pest. Totally, it's keep a long time. And submajor is a medium size, and the small size disappeared. The light green one, right? So many insect pests actually disappeared in your cropping system. So we think about this, and we have the policy to abandon some field, not always the cropping. So we investigate once, about this field. It was a different kind of cropping field, and it becomes this heath, right? And of course, right? And we collect very simply to find the insect, okay? Okay. And so many farmland actually abundant, and maybe also become a source of the rice pest in the next crop. So aside the abundant field, the insect pest injury becomes a serious more than others. So we think the policy is not good as enough, right? So some case Yeah, I will not consider because of time, so I just stop like here. But lastly, I have the very simple, different case. I just go through, right? Okay, so this is a kind of a different way of the insect living together. We are not to say attack or something. We are living together. If this way we say the cooperation, and this becomes decomposer, also the insectual, right? Okay. Yeah. The flower, and again, okay. Now we're talking about why the insect disappeared because of the cropping system. Okay, sorry. Okay, because of the swarming for the primary consumer, that we say that this is a community for the insect. So insect community is something like this one. So pesticides and whatever to cause the insect fauna, pest fauna change. So if you want to do this data, you have to collect all the specimens and analyze, and identification is the most important part. But actually, this is exhaustive work and time consumer, and also very special knowledge you have to spend, and you have to establish very good key or the identification act for to join this agro ecosystem study. So we look at this food system based on the ecosystem service, that's agro ecosystem service. So the service is not only you find what you need, you also have to take care, and you have to think about something you don't care, but you have to care. Okay, thank you.
Thank you, Dr. Zain. Though Dr. Zain exceeds his time limit, but he still showed us some insightful understanding regarding agricultural sustainability through an entomological perspective. Okay, I think he exceeded most of the time, but still maybe audience do have some valid and the very important queries or the questions. I request volunteers to provide the microphones for the questions. Anyone from the east side? Okay, I don't see any hands. So then okay.
Thank you very much. I enjoyed your talk, and also the very last this slide give us a very important message. So from this message that you are showing that insect pest has changed through the time period, and the main driver would be, do you think it would be the pesticide which change the insect food web?
Right.
So if that is the case, and what would be the future solution or future direction to modify or kind of manage this kind of
operation
case? Yes.
The corporate operation. Yes, actually, it was the report from the vulnerable of the biodiversity. Under climate change, the project, the big project, and they asked me why cropping. I mean the footprint and the plant is changed, but still, people use the pesticide. Maybe nothing changed, only the brand, only the different companies' product, but they still use the pesticide. So how comes we don't have, like in your country? I know you have the student come to Taiwan. They would like to learn something about our dean's specialists, the plant breeding. and say, oh, we have long time not seek. We only, we say the human selection, not the nature selection. And the human are not the farmer. They selected by the consumer. You know, we have really long time, you know, many kind of the fruit is sweet enough and people complain. So now they are not encouraged to, growing this kind. And in this way, how comes the insect, you have to kill it? Actually, this is not insect pest to your cropping, to your crops. And how comes you have to kill it? But actually, the other way they keep is we conserve some abundant area for the something non-related to our main purpose. I mean, not in the agricultural field. It's outside your operation, but they still spray, because of no choice. So this caused some insect because of the reduce of the host, I mean the food, and also you have the pesticide often, so they disappeared, right? So the fauna changed, and this way also happened in the nature history. We can find many species. Actually, it was very serious pest, but because of our agriculture change, so they also changed. Okay, thank you.
I'd like to introduce new presenter of the session, Professor Dr. Arjun Kumar Shrestha. He is the Dean of the Faculty of Agriculture at Agriculture and Forestry University, Chitwan, Nepal, and he is also the renowned horticulturist with expertise in fruit science, post-harvest horticulture, and protected agriculture. His research was focused on climate-resilient agriculture, innovative horticultural practices, and post-harvest technology. And he has been recognized for contributions in research, policy development, and mentoring future agricultural professionals.
Post-harvest loss and waste in horticulture commodity for a sustainable food system. And so I will try to cover the major, the methods that we are trying to do an experiment in our, the horticulture lab, and also we'll try to give some insight. What are the major, the innovative technologies, especially that are targeted to reduce the post-harvest loss in horticulture commodity in other laboratories. Sorry. So we often recommend to others that you should consume at least 300 grams of vegetable per day, and also the fruits at least 80 to 100 grams per person per day. This is our recommendation to become the healthy person. But I think you have gone through one recent news in Kathmandu Post. I think it was posted in 27 January last week, that about 5 or 6 quintal of leafy vegetables, they were dumped in the Kalimati wholesale market due to the higher level of pesticide residue in these leafy vegetables. And as a consequence, in this week, the price of the leafy vegetables, it was significantly decreased in the Kalimati wholesale market. And if you go through that, the article, you can find mainly 2 reasons for that. One, of course, now we will have the normal season of vegetable production. And another major reason behind this is that maximum level of residue in the leafy vegetable. So in the global context, we often talk about the Sustainable Development Goal, and especially that Sustainable Development Goal 12, and more specifically in the 12.3, it is a vital issue how to grasp the extent of food loss. As you can see, the recent studies, they have projected that the share of the lost and the wasted food could be doubled by 2050. And that emits 8 to 10% of global greenhouse gas emission. So this is the news article published in the US paper that the half of all US produce without imports that is discarded or lost. So this is the production data from FoA. More or less similar scenario exists in the developing as well as developed countries. I mean, there is a huge the loss, especially in case of the fruits and vegetables. You can see about it is within the range of 30 to 50%, depending on whether it is a developed country, industrialized Asian country, or the developing country. Now, this is the news article that was published in the Kathmandu Post, that there was a huge loss of manda that was stored in the Suntala super zone under the Prime Minister Irrigation Modernization Project area. So this scenario indicates that there is a huge post-harvest loss, especially in case of horticulture commodity. And whenever we talk about to feed and to ensure the food and nutrition security, you can see, as cited by AFU2020, that the amount and type of the food losses in the world is nutritionally sufficient to meet the demands of undernourished population in the world. And it can overcome the demand also. That means it can generate the surplus, provided that we adopt the proper post-harvest management techniques. So we can conclude that the world's food production is sufficient to meet the population nutritional demand worldwide. So this is the different, the article produced by the Nepalese scientists regarding the extent of post-harvest loss in fruits and vegetables. If you go through all these articles, you can find the range within the 15 to 50%, depending on the existing scenario in that particular location. Not only there is the loss, there is growing concern among the scientists regarding how to manage, how to reduce the losses. So if you go through the article about the food waste, food security and environmental impact, you can see gradual and significant increase in the research related to the food waste, food security and environmental impact. So this is the positive scenario for all of us, that okay, now the world is directed, all the activities or researches are directed towards minimizing the post-harvest losses. Whenever we talk about the post-harvest losses, all of us know that the pre-harvest, the post-harvest factors are responsible for the post-harvest losses. So this is one of the research that was carried by Dr. Roca in our lab, that the pre-harvest spraying of the certain plant growth regulators can reduce the decay loss in mandarin fruit. So the pre-harvest factor is also quite crucial whenever we talk about the post-harvest loss. It doesn't mean that the post-harvest factors are not responsible. They are also equally more responsible whenever we talk about the post-harvest loss in fruits and vegetables. So this is about the metabolic crosstalk. We can discuss how both the pre-harvest factors and the post-harvest factors are responsible, and looking at that metabolic crosstalk, we can talk about the current and emerging approaches to prevent the post-harvest deterioration of the fresh horticulture produce. You can see here, different approaches are there. First one is the quality, what you can say, for most important in the genetic background of that particular variety and species of the fruit and vegetable. And secondly, the growth regulators, like the inhibition for the ethylene generation within the plant system, edible coatings are there, pre-harvest growth condition is there, and there are so many, the controlled atmospheric storage, ultra low oxygen condition in the storage condition, physical treatments including the hot water treatment, essential oil. So this is all the approaches related to the prevention of post-harvest loss reductions are centered around this metabolic crosstalk. So whenever we talk about the plant breeding, of course that is quite crucial. Not only for increasing the productivity, you can see a lot of the researches related to the post-harvest losses, they are centered around in the tomato is one of the model vegetable crop related to the experiment or the research on the post-harvest loss reduction. You can see so many, the genes and the methods were used by the scientists in the tomato, banana, even strawberry, potato, apple. So these are, so this indicates that, this table indicates that the plant breeding, or you can say the biotechnological aspects, can be quite crucial, pivotal to reduce post-harvest loss in horticulture and fruits, in horticulture commodity. So you can see here one of the research that we have carried out using the hot water treatment. You can see over the control, there is reduction, significant reduction in the spoilage loss in the mango fruits. So this is about the pericarp browning problem that our lychee, the growers and the retailers and wholesalers are facing in Nepal. So with certain, the post-harvest treatment using the different concentration of the oxalic acid can significantly reduce that problem, along with reduction in the spoilage loss. So another issue, the research that was carried out in Forestry University, it indicates that the innovative and imaginative growing systems, they have been developed, especially related to the hydroponics. So whenever we talk about the pesticide residue label in the leafy vegetable, so that kind of the growing system can be helpful to reduce the post-harvest loss. For example, the IoTs, they are nowadays Internet of Things, and many the commercial companies, they are using this IoT. And also the integration of the LED lighting technology can be quite helpful in increasing the productivity of hydroponic system. So this is about another the approach that we can adopt whenever we talk about the reduction of post-harvest losses in fruits and vegetables like the apple. You can see here in case of the apple and also in the tomato, this kind of technology is an innovative approach so as to reduce the post-harvest loss. And novel packaging that includes the active edible films and the coatings, protective packagings are there, and also the intelligent packaging technology that monitor the condition of the packaged food using the data carriers, indicators, and sensors. So novel packaging will be another novel, the innovative approaches whenever we talk about the reduction of post-harvest loss in fruits and vegetables. So you can see here so many ethylene absorber or ethylene scavenging process can be used to maintain the quality of the fresh horticulture produce. So this is about the bioactive packaging. Whenever we talk about the active packaging, it may be the antioxidant, carbon dioxide emitters, antimicrobial agents, ethylene scavenger, as well as the oxygen scavengers are there. So we can utilize them into the food product through control or the fast release during the storage or just before consumption. So cold chain infrastructure, especially in our countries, can be one other approach just to reduce the post-harvest loss in horticulture sector. And for that, especially in our rural areas, solar-powered cold storage will be the best approach. And also, certain IoT-enabled temperature monitoring should be there so as to reduce the post-harvest losses. So this is one of the technology that is being practiced in Indian rural area. That is the solar powered cold storage is there, and also the IoT enabled temperature monitoring is quite essential. So these approaches can be even used in our case also. So not only this kind of the approaches to reduce the post-harvest losses, but we can adopt such kind of post-harvest processing technology, like the high-pressure processing, especially in case of the preservation of our fruit juice, vegetable juice. We can utilize this high-pressure processing techniques. Pulse electric field is there, and also nowadays quick freezing technology for the fruits and vegetables also help maintain the nutrient quality while preventing the losses due to long distance transportation. So this is one of the techniques, that is high pressure processing, that can be used, as well as the quick freeze technology can be a boon for our the horticulture producer. So nowadays any talk includes about the use of artificial intelligence and the machine learning, and that applies in the post-harvest horticulture as well. So nowadays there are predictive analytics for harvesting. So we can use the AI-powered tools so that the farmers can decide when is the best time to harvest our produce. Because the maturity index, identification and selection of maturity index is key for better post-harvest life of the commodity. And then there are smart sorting and grading system, especially in the developed countries. For example, in case of mandarin orange in Japan, there is such kind of sorting and grading system. Robotic case packing are there, and also very important is nowadays is for the blockchain for traceability. It is very important for the quality management aspect. You can see here how the AI-powered predictive analytics can be used for the harvesting of vegetables and fruits. And another figure shows the AI-based sorting and grading system for the fruits. So there is application of drones and remote sensing also, especially for the harvest mapping and also the logistic optimization. So the drones can provide the real-time monitoring of the produce in not only in the field, in the storage facility, that will help in tracking the humidity, temperature and pest infestation, allowing the timely intervention. So whenever we talk about the innovative packaging solution in case of the post-harvest horticulture, there is biodegradable packaging. For example, the companies like the Rapid Packaging, it offers the eco-friendly alternatives to plastic that reduce the waste and also protect produce during the transit. And MAP is very well known, the terminology for all of us. That is the modified atmosphere packaging that will help to alter the level of oxygen and carbon dioxide within that packaging system. Especially that will target to reduce the oxygen level and slightly elevate the level of carbon dioxide within that packaging. So, the Kalyanani madam is also here. They have done one research when I think at IAS. So this was one of the techniques that we can use. And another recent research we did in collaboration with Mandala Agrofresh, that you can see here the effect of MAP bags along with the ethylene absorber sachet. In case of the capsicum, you can compare the shelf life. In case of control, it was just 11 days versus that of the 23 days with the combination of MAP and the germinator seed. So you can see the almost double shelf life in case of capsicum that we have tried recently. More or less similar, the result we got in case of tomato also. So there are certain technologies that we can easily adopt in the farmers' condition also. And this is about the effect of packaging on the post-harvest shelf life and fruit quality of the capsicum under cool water storage. Nowadays, the cool water storage is very popular among the medium scale farmers and the small scale farmers. So this is one of the experiment that was carried along with the map containing different perforations. So it indicates that map is quite, the useful so as to reduce post-harvest life, not only in fruits but also in vegetables as well. So recently we have tried the nano zinc oxide also as a post-harvest treatment in our lab so as to reduce the spoilage loss of capsicum, and you can see a significant decrease in the spoilage loss using the nano zinc oxide at the rate of 200 ppm compared to that of the control. So the nano zinc oxide can be one of the another alternative solution so as to reduce post-harvest loss in our case. So I have gone through one article. See, what are the government initiatives, especially in India, so as to reduce the post-harvest loss? And I have found certain, the agri-tech platforms are there, like the Dehat, Kheti Badi, and also the farmers producer organization are they very, they active, and they are helpful in reducing post-harvest losses in India. So we can also learn from this kind of initiatives undertaken by the government side. So what will be the the roadways? What will be the further steps so as to reduce the the post-harvest losses in our case? So in my opinion, these are some of the the aspects that we should take our the initiatives. We should provide the research and experiments in these aspects, including the genetic and molecular basis of the quality traits, especially targeted to develop some kind of resistance to the post-harvest disease and the insects, integrating the available technology that we have, and also very important is we have to enhance the specific health conferring components in the fresh and processed products, managing the logistics and supply chain more effectively and efficiently. And more importantly, the last one is the most important one. We have to understand and manipulate the underlying metabolic system whenever we talk about our experiment or research targeted towards minimizing the post-harvest loss in fruits and vegetables. So, in conclusion, I must say that by reducing the post-harvest loss, we will not only secure its food supply, but also improves the farmers' incomes and contributes to the sustainable agriculture practices and, as a whole, sustainable food system. Thank you.
With this, I'd like to introduce our another presenter of the session, Associate Professor Dr. Rajan Ghimre from the New Mexico State University, USA. He's the director of the Center for Carbon Management and Soil Health from the very same university, as well as the chairperson of the Soil and Water Management and Conservation Division, Soil Science Society of America. And he has done his PhD in soil science, specialized in soil biochemistry. And he has been recently awarded by the Mobley Family Indoor Distinguished Research Award.
Thank you everyone for coming. Thank you, Udit, for this opportunity to share my work on soil health and carbon management for transforming agriculture and food systems in a changing world. So I would like to start from yesterday's discussion on the greenhouse gas emissions. That if you look at this picture, global greenhouse gas emissions has been increasing over years. This data of last 40 years shows that almost like every sector has increased greenhouse gas emissions in the global. And then if you look at the relative contribution of different sectors, it is up and down. Some sectors are increasing more, some other sectors are increasing a little bit less, but net greenhouse gas emissions has not gone down. And then if we look at the historic data, in last 200 years, we lost almost like 133 gigaton of carbon or billion metric ton of soil carbon that is lost to atmosphere. So that is net loss from soil and then added to the atmosphere. And if we look at nitrous oxide emission, just last 40 years, 40% increase in nitrous oxide emissions. And then that is more important because nitrous oxide emissions have almost like 300 times more global warming potential than carbon dioxide in 100-year time scale. So looking at these statistics and then added nitrous oxide and added carbon dioxide in atmosphere, that can impact our agricultural sustainability, agricultural production, both directly into the soil system, directly into production agriculture, or indirectly through other changes in the environment that affects agricultural production and agricultural sustainability in the world. So in this prospect, what I'm going to talk today is briefly discuss about what is carbon sequestration, how that relates to soil health, and then our initiative through this New Mexico State University Carbon Center, what we are working on different projects in New Mexico and around that area. And the key findings from these projects and implications, so I'm trying to link that back to Nepalese context, like how we can relate that, what we are working on New Mexico, how that relates to our context in Nepal. So just to start simply with carbon sequestration, we talked the last 100, 200 years, we released tons of carbon dioxide and other greenhouse gases to atmosphere that, simply using plants to capture that carbon and ultimately storing that carbon into soil is carbon sequestration. Sometimes the terminology looks fancy, but it is simply, the carbon lost into atmosphere, bringing that back to soil is a carbon sequestration process. But it is crucial because with this tons of carbon in the atmosphere, it is causing several changes in agroecosystem. So, and then, for example, changing our precipitation pattern, increasing temperature, and then which have a lot of impact in crop production, impact in plant production, and then soil functions, different ecosystem functions provided by soil. And then this increasing carbon storage is very important for soil health, which involves working on physical, chemical, biological aspect of soil. For example, when we talk about human health, we talk about our blood sugar, we talk about our body fitness, physical, chemical, biochemical conditions. Same applies to the soil. And then on that process, I think this carbon really works as the heart of the soil health system. So working on carbon actually improves that physical condition, chemical condition, biological condition of soil. And then that ultimately relates to different ecosystem functions. For example, soil erosion. Now that is related with the making soil carbon serves as a binding agent for soil particles, makes a good structure, and then with that good structure, water and air movement is regulated into the soil system, so that can reduce soil erosion. Same way, it provides habitat for diverse microorganisms, so it supports soil biodiversity. When you have a better structure, it regulates water cycle in the soil, so infiltration is improved. And then same way, nutrient availability. The carbon is not just carbon itself. As a part of the organic matter, it retains nutrients, then that regulates nutrients also. And ultimately reduce greenhouse gas emissions by sequestering carbon into the soil. So these are some of the functions. But sequestering carbon in the soil, we talk almost like everywhere in the globe. We talk about carbon sequestration, we can do it and we can revert climate change. But it's not that easy. We have been working on soil organic matter research, carbon research for hundreds of years, but still there is no reliable technology that we can quantify how much of the carbon we estimated. If you look at, maybe you can see 10,000 or 100,000 papers published about sequestering carbon. But still, there is a lot of variability in carbon estimation because of the inherent variability in soil, also because of the techniques we use, and then other environmental and other factors. So lack of technology is a major limitation, and specifically where I am working is part of the western United States, this western half of the United States. It's relatively dry, less precipitation, high temperature variability, and then associated with that, there is a high variability in cropping practices also. So on those diverse cropping environment, diverse condition, and limited by water and temperature variation, there is no quantifiable benefits, or the benefit we really want to see in 1 or couple years. That is not possible to see in those short time period. It takes 5, sometimes 10, that long time commitment to see quantifiable change in carbon storage. And then, although there is some policy, but location-specific, region-specific policy is lacking in different part of the United States also. And New Mexico, same way, we don't have a policy and economic incentive program that seems lucrative for farmers, that attracts farmers to adopt those practices. And ultimately, that is most important, having supportive policy, the correct quantification of the carbon, and then adoption of carbon management practices that is needed. So on this context, we work on the roadmap in 2022 to work on how we can make New Mexico, state of New Mexico as a carbon neutral. Then we work on this roadmap to work first, 3 years, first phase of the project to establish baseline carbon, to understand what is our baseline status of the carbon in New Mexico, and then develop education, outreach, and workforce development program around that strategy that we have a right workforce to work on regenerative practices, crop management practices, soil management practices. That is, they can adopt those practices or promote those practices to New Mexico farmers, ranchers, and all other stakeholders. And then we also look at, in the first phase, we established some research and demonstration site across New Mexico so that we develop those technologies. And then in the second phase, we implement those technologies in the wider area, and then in the third phase across New Mexico. That is a 3-step plan we prepared in 2022, and then that, as a part of that, we established the carbon center. And then what are those practices we identify? We almost like more than 20 faculty in College of Agriculture and College of Engineering. We gather together and then work on different practices that might be applicable for adopting carbon sequestration in different landscapes. If we focus on just an agricultural landscape or agronomic cropping system, minimizing soil disturbance, maximizing carbon input, increasing cropping intensity and diversity, and some of the frontier technologies like breeding for advanced crop, which have a deep-rooted cropping system, large and recalcitrant cropping system, so that the carbon degradation is slow, using biochar, biofuel production system, and then using those residue in the system. Those are called transformative or frontier technologies or next generation technologies for carbon sequestration. And then on this, through this carbon management and soil health initiative, our approach is utilizing more carbon per drop, because I mentioned earlier, water is one of the limiting factor for carbon storage in dry environments like New Mexico. So improving physiological efficiency, working on breeding approaches to enhance more carbon capture per unit water loss, working on crop physiology. And then physiology and breeding. And then, when we get more carbon into biomass, more recalcitrant carbon, then working on regenerative soil management practices, which is, I have been focusing on my research group, that putting that carbon into soil and enhancing that carbon storage into the soil ecosystem. So that is one approach we have been adopting under this carbon management initiative. Another is putting that carbon into food water energy nexus, linking that carbon into livelihood of farming community. That is another way to put that carbon as a part of your daily life. That way you can enhance carbon storage, and then the more and more farmers can adopt those technologies. So that is another approach, and we are implementing this strategy on these projects. On this project, we are actually covering all ecosystems in New Mexico: forest ecosystem, rangeland ecosystem, rangeland ecosystem, forest ecosystem, urban ecosystem, and typical cropland or cropping ecosystem. And then to implement those different practices, we are implementing different cropping strategies. For example, agroforestry management in one of the research center, forest management in another center, crop livestock integrated system, how livestock integration can help or hurt carbon storage, forest management, cover crop, and then different land use, looking at the rangeland, different amendments. So across New Mexico, out of 12 science centers across the state, we are implementing these practices into 7 different places, targeting on different ecological zones. For example, this is 6 different climatic zones across New Mexico is covered by this project. So that way, we will have a comprehensive data set and different temperature regime, different moisture regime, different soil type, and different agro environment, as well as different cropping systems. So that way, we collect more than 600 soil samples from these different sites, management data from those sites, and then all soil health and carbon data from these different locations. So we are collecting that comprehensive information to understand how these different systems are responding to carbon management. On each of these sites, we have one typical agricultural practice and at least one alternative or regenerative management practices, so that we know if those alternative technologies in the forest management, cropland management, rangeland management is working or not. And then not only in New Mexico, I am working with other colleagues in Colorado and other area like Texas, Colorado, Kansas, this area, covering, linking that carbon storage with other soil health functions. For example, involving students to learn about how to measure different soil properties in the field, looking at some macrofauna in the lab, and then linking that with crop production, water dynamics, soil health, all those different aspects we are looking on this project. And then in case of frontier technology, we are modifying biochar. You can produce biochar, and then I'm working with agricultural engineers who modify those biochars to aid nitrogen, phosphorus in a certain amount, and then in a certain chemicals, so that release of those nutrients from that biochar is regulated into the cropping systems that you like. And then another approach we are working is using perennial crops. In US, you might have heard instead of annual wheat, we breeders have been developing a perennial wheat crop, perennial sorghum crop, perennial canola, so that you plant once and then it keeps growing for multiple years, so that the root system is contributing more carbon, more nutrient, and then regulating those soil cycles more robust as compared to annual cropping systems. And so we are integrating that aspect as well in this project. So now I will like to go, these are the few initiatives as a part of this carbon management initiative in New Mexico. And then there are multiple projects you see, and I would like to share some of the findings from this different projects. For example, we have been working on cover crop for a long time, and as a part of this carbon and soil health strategy, we look at different carbon fractions, where carbon is going from legume cover crop versus non-legume cover crop versus mixed cover cropping, and then how that carbon is storing, how long that can stay in the soil. Is that more labile carbon, or that is stable carbon, or how that works, how much of the nutrient is releasing from these cover crops, and looking at that, we could see some of the nitrogen limitation. Nitrogen is going down. That means nitrogen is limited in the cropping system, but in case of carbon storage is increased, both in the form of stable carbon or more labile form of carbon. The magnitude of storage is a little bit different in different systems. And then not only carbon storage, we look at the mechanism. What is regulating this? Whether that is a soil fungus, soil bacteria, or some other chemical components like soil pH as a master variable. What is their role? How they are working? And then how that is linked with different soil functions, carbon storage, crop production, biodiversity regulation. So that is really critical when we talk about sustainability, not just looking at the soil response and then getting the carbon storage more. We need to go beyond that. How that is linked to our biodiversity management, maintenance, carbon sequestration, crop production. Because when we go to the farmers, ultimate question it comes is, what is there for the farmers? Because carbon, you don't see that. So if it is not linked with crop production, then maybe this technology might not work. And then we look at, beyond that, we look at carbon storage. We look at greenhouse gas emissions, how much is lost from the atmosphere, and then linking that with economics. With the current market price in carbon market in US, we look at the lowest minimum price and then look at these cover cropping systems. We see at least like $47 to $90, $40 to $50 to $100 gain with adoption of cover cropping practices or more diverse cropping systems as compared to crop fallow based cropping systems or cash crop and leaving land fallow. That is not sustainable in our system. So that is one example. I look at multiple components and then looking at sustainability or soil sustainability aspect of these cover cropping system. And we also look at other components, not just the cover cropping. We had another project looking at compost and manure management, and you could see the difference in these, C0, no compost application, 3 ton, 6 ton, 9, 12, and 15 ton compost application. It's really changing the root dynamics. Look at the root mass, how much root is aided with adding more compost. So looking at those, you can see the compost addition have an important role in sustainable agriculture, that it stores more carbon. Not only more carbon, when you have more roots, it can use the nutrients more efficiently. And then maybe other ecosystem functions also regulated by roots. And then same way we look at microbial community on this project with compost addition versus no compost addition. We look at significant increase in fungal community. Saprophytic fungus that include some pathogenic but mostly beneficial fungal community is increased with compost addition. And then you see over years, those bubbles are moving. That is with compost aided system, that is moving into more beneficial community as compared to no compost system. And then another approach, that could be relevant to our context is we did one work with livestock integration, grazing livestock in winter season, and our traditional cropping system in Nepal also, that winter grazing is common. Maybe in the high mountains, middle mountain regions, that is still common in some areas, but in US, that is predominant practice in arid and semi-arid West. December, January, February, they graze cattle into crop residues. And then looking at soil sustainability component, soil health component, including carbon and then some other microbial communities, some nutrients, we could see, I have the carbon data, that carbon storage in top 20 centimeter soil is higher with livestock integrated conventional tilled system as compared to no tillage. Because in soil we promote no tillage, minimum tillage, but having livestock, grazing cattle first even 3 months in a year is more beneficial than adopting no tillage. So that is a very interesting finding from our work in livestock integrated system. And another is redesigning our agriculture. That is another innovation we did to improve carbon management. That you might have seen in US. Majority of the area have center pivot irrigation system, overhead center pivot that goes around the circle and then irrigates the crop field. But because of the lack of the water, we run into a situation that we did not have enough water to irrigate the whole circle at a time. So we redesigned in a way that introduced native grasses into 30-foot strip, and then crop in the 60-foot strips, so that you can grow 2/3 of the area is still used for cash crop production, and 1/3 of the area is transformed into native grass system. And then we look at multiple ecosystem services, not only carbon. Of course, my focus was looking at carbon, looking at the below ground dynamics, how it changes soil aggregation, how it changes microbial community, how it changes nutrients. But also, we look at above ground biodiversity, traffic use. When you have a grass on there, you can drive tractor. If you run into situation to fix the irrigation pivot, that grass is a buffer zone. So that is another approach to enhance sustainability when you need to face with the limitation, because the water was the limiting resource, and then we wanted to change that constraint to the opportunity that you have a native grass which you can graze during the if you have a limitation of forest. And then that is also linked to some of the work we can easily do. And then I worked, it is maybe 10-15 years ago. This is Eastern Chitwan. I worked on that sloping agricultural land technology, or using vegetative buffer to control erosion. And then that is exactly what we are doing here, but in the different systems. Why I am bringing these pictures, old pictures, is we need to develop context specific. Our landscape specific technologies, maybe the principle is same. We are using, water and wind erosion, maximizing water use. But in our case, water erosion, landslide is the major issue. And then using the vegetative buffer. Right buffer is same technology we have been using, we have been developing here to work on it to enhance the sustainability of production system. Then another is, using biochar, because biochar, I see some of the soils students here also working on biochar research. What we are doing is using biochar as a soil amendment so that you can store carbon for hundreds of years. Because biochar is resistant to, when it is prepared in the high temperature, because of the high temperature, its resistance to changes in biotic and abiotic force is reduced. So it can last into hundreds of years. And then looking at different aspects, you can see, we are measuring greenhouse gas emissions here, multiple soil sampling, monitoring crop yield. As a system, we are monitoring what is the input and output balance in these systems. And we could see that some of the biochar we modified, our collaborators modified and then used in the cropping systems. We could reduce up to 70% nitrous oxide emission is possible using biochar, slightly modified biochar. That is possible. And then those biochar stay for a long time. So once you apply in the field, once you apply in your farm, it can stay 10, 20, 30 years. That it really helps in increasing carbon storage. But at the same time, when we look at the water infiltration, that limited water we get, because of the stiff soil structure, we lose some of the water in this dry environment. Sometimes, too much heat, it creates hydrophobic soil environment, and then that water gets lost. But when we apply biochar in cropping systems, we saw almost like a 3 to 5 times increase in water infiltration capacity. So water storage is increased. Then when you have biochar crystals apply in the soil, that makes the soil structure loose. And then when you have a root aeration, air and water balance in the rooting system, that also enhance crop productivity. Biochar doesn't necessarily provide nutrients, but providing other changes in the soil environment, it can support better crop growth and better productivity. That is another aspect. And what I really want to emphasize, in the research, we have tons of data, but a transforming agriculture is rooted on, transforming those technologies to the farmers. So we need to really not just the research center data. Yes, I get 70% change in nitrous oxide emission, 50% change in carbon dioxide emission, and then storage in carbon 10 to 20% increase over 2, 3, 5 years. But that technology really need to be transferred to the farmers to get mass benefit in case of transforming agricultural system and improving sustainability of the system. So working with farmers, either bringing them to your research plot, research center, bringing them to university, or going them to on their farm and then really talking what they are facing, what is their issue, and then how this transformative research can be translated into farmers' field is really critical. And then we work on that aspect as well in New Mexico to see real field impact in farmers' field. So that is, now we move into implication for Nepal. I just, after I got invitation, I started looking like how I can relate this work, because I'm working on more water limited environment, how I can relate with the Nepalese context, and then got some of these pictures we collected. It is almost like 10 to 15 years old pictures. This is Lamjung district, this is Nuwakot, and then this is here in Chitwan district when I was working here. And then this represents our different landscape, different cropping system, different farming systems. Like New Mexico, we have or even more diverse environment in case of Nepal. Climatic diversity, soil diversity is very high here. So we need to work on those strategies that really works on those diverse landscape. So in case of soil carbon data, that was one of the work we did in South Asia, and then specific another work I cited that was recently published looking at soil carbon distribution in South Asia. You can see if you look at Nepalese context in South Asia, we are a little bit better positioned. Our soil have a little more carbon storage than rest of the South Asia. But if we look at a different part of Nepal, then Tarai to middle mountain in medium condition, and then high mountain region really low in organic carbon storage. And then the carbon management, soil health, and agricultural sustainability strategies should be made based on those soil variations so that we can get maximum out of this environment. And then in a recent, this paper was invited by Agronomy Journal. They wanted to look at carbon storage with regenerative agricultural practices. And then we did review for Nepal and broader in South Asia region. Then I bring this table from there. Mostly the study is done in southern part of the country. We don't have many studies done in middle mountain, high mountain regions of the country. And then, but still we can see some increase in carbon storage with no-tillage, crop residue management, farmyard manure management, and crop residue management practices. But what I see as a major research need, looking at this is just like a glimpse of data, diversity in our agriculture. We also don't have a benchmark carbon status on our soil. These, the map I showed is mostly the remote sensing based information. And then that remote sensing based information should be validated, like what we are doing in New Mexico. I think that could benefit for Nepal also, looking different agroecological zone, looking at the carbon status and different cropping systems. That might be crucial first step to enhance soil sustainability and agricultural sustainability in Nepal. And then region-specific soil health and carbon management framework, because if you look at eastern to western and then south to north, there is a high variability in our soil, in our ecosystem, crop systems, vegetation type. So we need that region-specific strategies. We cannot apply that one blanket application or blanket recommendation to enhance soil health and carbon management, and ultimately that is linked to agricultural sustainability. And optimizing cropping system and management strategies, like working on crop rotation, diversity, amendment, fertility management, that also need to be updated. I don't know the recent status, but until last few years, we were using 1980s recommendation for our cropping systems. And then after 40 years, we are using that 40-year-old recommendation. Our varieties have changed. Different crop varieties have changed, climate have changed, soil status have changed, so that the recommendation should be updated to enhance agricultural sustainability. Grazing management in high mountain region, because I see a couple of pasture degradation studies, pasture degradation reports in high mountain regions. We need to really work on those also to enhance agricultural sustainability and engaging local community on these tasks. Now, research, we can generate data, but engaging community is crucial if we are thinking of sustainability or transforming agriculture. So in conclusion, look at our complex cropping system, integrated nature of our farming system. And then these, yesterday we were talking a little bit about, corporate farming, and then the big scale farming. With that change, we need to redesign our farming system, that this crucial component of integrated nature of our farming system should not go away with those modernization in agricultural systems. And then soil and carbon management is a key for transforming agriculture. Soil is the foundation, so that we need to think of that. And then we need to develop strategies using system approach, not just like a soil-centric approach, but our agriculture-centric and economy-centric approach will be the best way to enhance carbon storage, both in New Mexico and in Nepal. So I think with that, integrating multiple technologies is good. And then this all work is dedicated to my graduate students, postdocs, and researchers in my group. And then funding agency, a different funding agency provided the support to establish this program. That I would like to stop here. Thank you.
Thank you, Dr. Our next key presenter of the session, Dr. Madhav Prasad Pandey, Professor at Agriculture and the Forestry University, specialized in plant breeding, genetics, and biotechnology.
Thank you, organizers, for inviting me to present my work at AFU on wheat breeding. The title of my presentation is Wheat Breeding for the Future in the context of national scenario and our work at Agriculture and Forestry University. I will be briefly covering the national wheat production and trade scenario, breeding challenges, wheat improvement work by National Agriculture Research System, and in the context of future breeding challenges, I'll be talking our work at Agriculture and Forestry University. So, we all know that wheat is one of the important crops for human being, because it's among 5 founder crops of, that means these are the crops responsible for human civilization. So it dates back to almost 14,000 years as far as the documented data are, and world most widely grown staple crop. It is grown to the widest latitude around the globe. So it is grown on the cold, temperate areas as well as warm, humid areas. So quite a adaptable crop, and provides almost 20% of calories and protein in developing as well as developed countries. And to note is a 60% increase in wheat production is required to feed the human population by 2050. So this is brief highlight of nutritional composition of wheat grain. I can show you, it is, although we, in terms of nutrition, it is mostly these days eaten by diabetic people and those who wish to lose weight. So not eating rice 2 times a day in our part of the world. But it has not only that calorie and protein, there are quite a bit vitamins and other minerals and compounds that are beneficial for our health, like the betaine and choline are 2 compounds that are beneficial for cardiovascular disease. But to notice that these all most important nutrients are on the outer part of the grain. So when we use maida and the processed flour, then we lose this. So take-home message is better eat whole grain. So then you can get really the benefit of wheat. So this is brief global statistics of wheat production. The India and China, India are, along with the Russia, are the top wheat producer. And China, India, they are also the largest consumer of wheat. You can see on the second top, Nepal and Bangladesh. So this shows that the total wheat production is important for the food security of the world. And these are the global wheat export players. Among these, Russia, Canada, Australia, and United States are big players, along with the European Union, that includes many countries. So the China and India are the biggest producers, but they are also consumers. So that's why this, in the players, these countries determine the wheat market. And if you recall, 2 years back when Russia and Ukraine, the conflict started, then wheat price was up, and there was a hue and cry in the international wheat market. This is the wheat consumption pattern. You can see yellow, red encircled graph in the graph there showing the wheat consumption pattern in Nepal. It is annual consumption per capita is around 50 kilo, which is less than the global average as well as the Pakistan, and higher than Bangladesh. Of course, Bangladesh, they eat more rice, I guess. So the trend is increasing, and I think still will go some figures up in coming years in Nepal. So that putting more demand for wheat grains. So this is a AI-generated picture. I want to wanted to highlight the importance of wheat. I wrote that its contribution in GDP for food security, etc., and I gave this kind of results. So what it can tell us, let's see the area production productivity trend of wheat in Nepal for the last almost 10 years. So the land is steady but slightly decreasing, the area, and the production you can see in the okay, it's not visible on the LED. Okay, in the 2016, you can see dip in the area as well as in the production. This was a dry year, and 2020, it going up a little bit, a hip. Again, it's a good year for wheat crop. And if you see the trend, the area production and productions are a little bit going down, but the productivity is steady. So this shows there is an effect of new varieties, productive varieties coming in the market. So this is the overview of wheat import and export in Nepal. This is a quite unstable phenomena in Nepal. About 96% of the wheat demand in Nepal is met by home production or the country's production, but because of the industry demand, the wheat is often imported and also exported. And if you see, wheat import is mostly from India, almost 90 or more percentage. And in the export, Japan and Malaysia are the growing market for Nepalese wheat. And there are other countries where Nepalese wheat is exported. In some cases, it's a few 100 kilograms, and in some cases, like Japan and Malaysia, it's a substantial amount of wheat is exported. So in just 2025, just 2 weeks or 3 weeks ago, there was a announcement that the government is asking traders to import wheat, and Indian government, they approved 200,000 metric ton of wheat to export to Nepal. So this shows the trade value of the crop. And now coming to the wheat production challenges. In my opinion, the lower yields in farmers' field are the number one challenge. The elevated risk of biotic, especially the rust. We know rust are very important diseases. There are 3 kinds of rust: leaf rust, stem rust, and stripe rust. They cause significant loss. So this in biotic component rust disease, and abiotic stresses like heat drought and excess moisture particularly during early season, early crop growth, when there is a off-season rain, then wheat is, the crop is, the crop suffers and there is a yield loss. The another part is subsistence nature of farming, unstable supply of production inputs. This is a rather general challenge, and shrinking arable land and wheat acreages. In the following slide, I want to highlight the total arable land for the last almost 60 years in Nepal is declining, particularly onward 2001 or 2002, at the beginning of this century. And recent trend is the total arable land is declining in Nepal. And if you see the wheat area, it's also declining. Wheat area is declining there are multiple factors, but to sum up, this again puts pressure on the production and supply of wheat grains in Nepal. So, coming to climate-related hazards, I was talking about the wheat production challenges, abiotic challenges. These are the drought and heat stress particularly, and here we can see the prediction, the projected change in average annual precipitation and annual temperature. You can see on the blue, this map on the left, that this is for the precipitation, and the change in precipitation is more likely in the eastern, mid, and even midwestern part, whereas change in annual temperature is more likely in the western part, and also in the Tarai region, where the whole region is the wheat basket, the major wheat production area, so that will definitely affect the wheat production in Nepal. So here, the biotic factors as a wheat production challenge, you can see some reports. The successful surveillance result in early detection of UG99 in South Asia, that was actually in Nepal. And UG99 is stem rust race, which can break down the major stem rust resistance gene, and that created a international, global alarm in the wheat research community to the farmers, and there are a lot of initiatives going on to tackle this problem. And similarly, for the striped rust, the whole Himalayan region is the hot spot of striped rust race evolution. You can see on the far right, wheat pathogen strain in Europe from Himalayan region. So our new pathotypes are even, migrating or flying onto the European continent, and this is the concern for not only for our wheat crop, but also wheat crop around the world. So these are some proof I want to show here that because of the, so to say, climate change impact, if you believe in, or if you have the data to show that the disease dynamics is changing. You can see the leaf rust is usually a disease in the plain area, the major problem in the plain area, and if you go towards north, it is less problematic. But in the recent times, some virulent races are been reported that can affect crop in mid-hills, even in some high-hill regions, like the rust pathotype number 1, plain and high-hill, pathotype 3, plain to mid-hill, and the others from 6 to 10 are contained in the plain area. So this shows the changing dynamics of the leaf rust pathogen in Nepal. And similarly for the striped rust, it is basically the disease in the cold area in the north. Now it is coming down. So the virulent or the aggressive pathotypes are discovered that can go even in the Tarai plain area, Tarai and plain, especially number 1 and 2 pathotypes in all provinces, Lumbini, Karnali, Sudur Paschim, Bagmati. And this is another alarming report is the PSTS16 lineage, which is highly virulent striped rust race, has also been reported from Nepal. So this all together put tremendous pressure on wheat production. So to see the wheat breeding activities in a summary view, the wheat varietal development has been highly successful and rewarding. And we must acknowledge that our national wheat breeding program at Bhairava and in Kumaltar, these are among the strongest and highly impactful breeding programs in South Asia in the past, and still they are highly competitive breeding programs. Around 96% wheat demand is catered by the varieties and the technology developed by our research programs, national research program. And in recent turbulent global wheat supply markets, warned the buffering capacity of required buffering capacity of our nation to stabilize the future wheat supply. And future challenges lie due to stagnating yields, disease risk, and climate adversities like frequent drought, heat, and etc. So what about the national research system for wheat breeding in Nepal? In an overview, the national wheat breeding research programs are basically engaged in varietal development, following conventional method of hybridization, selection, introduction, very basic methodologies. And can see the non-consistent variety outflow and average yield potential of the developed varieties, which is around 5 to 6 ton average ton. This is the genetic potential. And if you see in the farmer's field, it is 4 ton around if it's in the good, the crop is well managed. Breeding for wider adaptation. Generally, our varieties developed by national wheat breeding programs are widely adapted. So one variety can be grown in different environment, different regions. So this is a very basic, the attribute of wheat varietal varieties in Nepal. However, in the cost of high yields, because we know that genotype interact with the environment. So GY interaction, if we can tap that, we can take the benefit of GY, where some specific varieties we can get higher yield in some environment and they perform poorly in other environment. But if we select for a wider adaptation, then we lose that advantage. As I talked earlier, the National Wheat Breeding Program lacks modern and emerging breeding technologies. They basically rely on conventional methods. And breeding objectives influenced by international collaborating partners. This is, I put a question mark and let you ask whether this statement can be made or it is wise to say so. You see here, this is the variety outflow in Nepal. You can see that the trend is like boom and bust cycle. So in the last 60 years, you can see 3 slightly growing, fall, growing, fall, and in 2005 onward, every 5 year, 2, 4, and 19 and 21 in 2 years, there are 10 varieties released. So if in a healthy breeding program, how it is possible? This is my question. So I assume that there are some influences from our collaborating partners and the flow of the genetic material, I must say, that influences our national wheat research program, wheat breeding program. So with this, we can see the gap in wheat breeding activities in Nepal. So partly, and this gives us opportunity to start or to initiate wheat improvement research at Agriculture and Forestry University. So this is the goal of we set at the beginning of wheat improvement research at AFU. To highlight is the two streams of varietal development for the stress environment as well as the normal high production environment using latest breeding technologies. So how far we are able to use such technology, I will show you in following slides, but this was the goal we set at the beginning of inception of the wheat improvement program at Agriculture and Forestry University. We follow two breeding portfolios. The first one is enhanced heat drought tolerance with yielding ability, disease pest reaction superior or at par with the standard check. And second portfolio is for high yield, high stability, better disease and pest tolerance. This is for commercial production in the non-stress environment. So breeding strategies were the introduction of international nursery, advanced line and germplasm, and home developed breeding materials by hybridization and selection using contra-season nurseries, selection aided with physiological traits, root traits, and DNA markers. So this is the research network because we had nothing in hand when we started with breeding research at agriculture at our university, because our university is or was also a young university recently established, and there is no breeding research or such a large scale research, premier research in the university or in academia. So we made a field network of research base and satellite station where repeated year breeding trials were done, and some farmers field site where single season or two season researches were done, so that we have the multi-environment, multi-year data enough to validate the performance and stability of our material. So this is a picture of our wheat breeding field at agronomy farm. This is a satellite station in Alprasi. We rented a farmer's field and used it for 2 years to generate breeding related data. So these are the accomplishments. So far we are able to identify two candidate varieties, AFU 001. The technical working name is MIT24, and AFU 002, MIT08. And recently we signed a MOU with a private seed company to help us for seed production and varietal development. And there are other companies also showing interest to join us to help us in wheat breeding, as well as looking for other frontiers for crop improvement. We developed around 6,000 advanced and segregating lines targeted for high yield, drought heat, stress tolerant, and rust resistance. These lines are actually growing in our field this time. So if someone is too much interested, I can show these lines in the field. We genotyped wheat varieties and breeding lines for important traits, QTLs, and supported thesis research of approximately 25 master's students. That include students from plant breeding department, students from biotechnology center, and from agronomy department. So this is a proof of performance of our candidate varieties. You can see this is the data from 2021-22 wheat season. So this includes quite diverse environment, and to note that all these materials from the very beginning we tested in two environments within the location. That is standard sowing date and late sowing about 4 weeks. So this gives us a 1 month window of sowing and see the genotype or these lines, how they perform, so that we can relate. If there is a delay in showing, then the genotype perform well, or the final product we can use for late showing as well as. Because in the Tarai and some part of inner thrice, because of rice crop, when a rice harvest is late or there is a rainfall during the wheat planting time, then wheat showing is late. And it has a constraint of high temperature, growing high temperature. So when we show wheat late, then we lose yield because of the high temperature, progressive high temperature after flowering time and critical grain filling time. So you see the D1 is the timely shown and D2 is the late shown. And these are the environment, and you can see in the favorable environment, MIT8 in the research plot 6.5 ton, 6.1 ton for MIT24, and overall average of 4.1 and 3.9 respectively for MIT8 and 24. And if you see the environment, like the these highlighted columns, Khajura D1 and Khajura D2, you can see these are the Khairani D1 and D2, and Hardinath D1 is the rainfall. This is waterlogging. There was a waterlogging situation, so overall performance was very poor. And in the Khajura D2, this was late shown in Nepalganj area. So the crop faced extreme heat and heat wave. So the overall, the average of these all lines were 2.6, whereas the selected candidate varieties, MIT8 performed 4.4, 3.1, and MIT24 2.7. So this shows that these candidates, they can perform relatively better under late shown heat stress conditions. So this is the stability, performance and the stability analysis. This data were for 3 years across 23 environments. So our MIT, this AFU W02 and W01 are performing better as well as on the stable lines. So this is the coleptile length, another important trait, crucial for early establishment and seedling vigor. We compare this with the standard varieties like Banganga and Vijay. And in this, I must say that the coleptile length is shorter than the standard. This Vijay is itself is a mega variety in Nepal. So with this, the showing depth, we can say that 6 centimeters is standard showing depth. If we seed deeper than that, then there will be problem of emergence in 2 candidate varieties. So this is the overall soil fertility optimization study. Here we try to simulate more practical environment rather than optimizing nitrogen, phosphorus, or potash in individual component. So L1, L2, H1, H2. L1 is a marginal type of environment. L2 is a superior farmers field environment. H1 is a research field environment. S2 is the luxurious environment. So with this, you can see MIT8 and MIT24. The L1, Banganga is performing better. It is a widely adopted and stable variety, released about 10 or 12 years ago. It's similar to BJ, but less liked by the farmers. And when the fertility, soil fertility enriched, L2, H1, and S2, then our variety they picked up. And all the way S2, the highest yielding is MYT8, followed by MYT24. So this gives an overview of how our variety respond to overall soil fertility management. So these, our varieties are basically for medium to high yield environments. So with heat stress, delayed sowing, this perform better. So summarizing the UPS of our candidate varieties, W01 is highly uniform, look really nice, has a longer stay grain, high yield and favorable environment as I earlier discussed about, and it has high protein, about 12.5 or so, compared to other varieties, Bijay and Gautam. It has high protein content and good for late sown condition too. Harbor APR adult plant resistance genes LR46 series, LR67, 68, and another pleiotropic gene LR37, YR17, SR38, and GLU-D1. This is the gluten gene, important for bread quality. Similarly, FU02, it is high yield under late sown heat stress condition, longer grain filling duration. This is a typical trait of this variety. The heading time is early, and the maturity time equals to MIT 24 or Bijay or even Banganga. So this gives a longer duration for grain filling, which is an important trait for high heat stress adaptation and late sowing conditions. And this also harbors important leaf frost resistance gene like LR46, 68, and GLU-D2. So this is the picture of AFU W01 in the research field of Rampur, AFU agronomy farm. The grain, this is the AFU W02, MIT8. And this is in the farmer field, W01. This is W02 in the farmer field in Kapilvastu. This was the previous season crop. The farmers, they produced seeds and tested variety for us. And this is the in-use quality assessment, Chapati organoleptic test. Interesting, you can see our teachers as a evaluator in there. So comparing with this test, Bijay is highly liked by the farmers for its chapati and overall quality. It is a mega variety, and there are a lot of stories about Bijay. So we use that as a check. And in terms of test, W01 is slightly better, and 8 is slightly poorer than the Bijay. Color, it is the creamy color is the superior one. So 08 is better. In terms of aroma, W01 is much better. So that gives a specific flavor of the cooked chapati, and chewiness, tearing is, and stickiness. So these also our varieties. In some cases these are superior. In other cases these are comparable to the standard check. So now coming to what I call using the latest breeding technologies in the goal, the earlier slide. So we try to use genomic tools in the wheat breeding program at AFU so that we can select earlier, we can select more specific, and we can make the whole research and the selection process more effective and efficient. So we use SSR marker for identity, diversity assessment, and gene tracking, CASP, STS, SNP, Indel for diagnostic gene tracking, and mid density genotyping for genotype fingerprint and gene tracking. So these are the results. Some pictures I can show. This is the SSR genotyping. So we have the SSR genotype of our variety along with the reference varieties. This will be useful for the varietal registration and release process. So this gives also our material AFU02 and 1 give a slightly different pattern than the mega varieties like Gautam, Bijay, and Banganga. Here, this is the picture of SNP genotyping. These are the diagnostic SNPs. We took help of Excellence in Breeding, CGIR initiative, Excellence in Breeding. They genotyped our material in 2020 and 2023. That was very much helpful to explore which genes are present or which allele profile is in our cultivar pool, Nepalese wheat cultivar pool, and which we are new in our material. So this is a genomic relatedness among Nepalese old and modern varieties and AFU candidate varieties. You can see the Gautam and Bijay are in a different cluster, and then MYT 24, 28. This is the mid-density genotyping. It's kind of neutral markers, totaling 3,182. And the more recent varieties like Jingong 2 and Borlag 2020 and our materials are more related. There is Jingong 1, and the old varieties or the popular varieties like Gautam and Vijay are rather distantly related in terms of genome. And on the right, these are the trait-based marker actually linked to useful traits, and that were total about 400 trait-based marker. That again gives a similar patterns of overall clustering. However, in terms when you come to MYT 24 and MYT 8, our candidates, then they are put together here in neutral marker, and trait-based they split. So this shows that these two candidates have different trait background. They are selected for different purposes. So this shows us overall genomic identity of Nepalese old historical cultivars, breeding lines, and our material. So a foundation for further genomic research or marker application in wheat breeding in Nepal. So these are the target traits. Based on the earlier SNP genotyping, we selected these 7 genes. 4 genes for leaf frost resistance. These are LR34, LR46, LR67. These all are pleiotropic genes governing leaf rust, stripe rust, powder mildew, and stem rust. LR68 is a single gene. And DREB 1B, it is drought and abiotic stress tolerance. Another abiotic stress tolerance, FESW3. And CRE 8, this is cereal cyst nematode resistance gene. We optimized 5 genes highlighted as optimized. So we have the marker assays and the protocol for screening this gene in any wheat genotypes. And these 2 genes we are optimizing this. And with the combination of these 7 genes, if we can use markers for the selection of breeding materials, then we can save time and resources for the development of wheat varieties. So this is the marker assay for LR34. You can see clear. This Bijay carries this gene, and the Borlag, and these 2 are not carrying. LR44, our material have LR44, another major gene for leaf rust, but this lacks Bijay and Bandganga, Borlaug, they lack this gene. And this is a summary of marker analysis on selected genotypes. The BJ, our two candidate MIT24, which is AFU001, and MIT08, AFU002, Bandganga and Borlaug. And this 6 gene, LR46, the two markers for LR42 flanking markers, LR34, 68, 67, and DRBB1. 1, 2, 3, 4, 5 genes. These are well optimized for marker-assisted selection, and we know that which genotype has this gene and which not. So with the help of this, we started another research to stake 5 genes in a single genotype so that it is more disease resistant, more drought and heat stress tolerant. So with this, a population was created with the major APR genes and abiotic stress tolerant DRBB1. The cross ID is C0221-01. This was, we have already F3 plants and progeny rows carrying 2 or more recombinant genes. And marker-assisted selection, F4, F5 progeny identifies the plant carrying multiple desirable genes, which lines with this LR34, major leaf rust resistance, pleiotropic gene, LR46, LR68, and another important gene for abiotic stress tolerance, DRBB1 gene, will provide near immune durable leaf rust resistance and abiotic stress tolerance. So this is the results of marker-assisted selection in the C02101 cross. On the top, you can see the parent A and B. This is for the builder's right. I anonymized the parent name. And if you see the F3 progenies, the green highlight you see, all 1, 2, 3, 4 genes are type cut? Okay, thank you. 2 lines, they carry all 4 genes. So this is like one LR34 and LR46 plus DREB. So this gives us a near immune leaf rust resistance as well as abiotic stress resistance. And there are several lines carrying 3 or 2 desirable genes. So we can select this by using these markers, select earlier at the early leaf stage in let's say within 1.5 months or 2 months, and then we can discard undesirable material and track only the desirable ones. So coming to the conclusion, in the history of approximately 60 years agriculture education in Nepal, breeding research within academia, let's say AFU, demonstrates success and future promises. I hope I was able to convince you that with the given results, we can make this statement quite boldly. With research varieties like AFU001 and 2 and other lines developed by AFU benefit Nepalese farmers, still not very much. This year we distributed around 3,500 kilos of 2 candidate varieties free of cost to our farmers, and we'll be visiting those fields. So it really, gives us a tremendous pleasure to give something tangible from our university to Nepalese farmers. And the scientific knowledge and expertise, marker tools on wheat breeding are highly relevant to national wheat breeding programs, and we are actually thinking and partly organizing already in the process of discussion. I have already talked to our VC ma'am and registrar and Dean, Faculty of Agriculture, about to organize a technical workshop to train and to show our expertise and the marker estate selection methods to National Wheat Breeding Program and other companies whosoever are interested. And breeding research at AFU was instrumental for the student skill development and postgraduate thesis research. I can tell you it is partly good thing and partly a little bit sad thing that when we train a better student, they fly earlier. You know, they go to US, they go to Australia, they are hired earlier, they get PhD earlier. But just the other day, I got a call from one of my students that my professor is asking, what is your professor doing there these days? So this is another satisfaction, you know, that while working in Nepal and under such resource limitations, not money, but other resource limitations, sometimes, you know, the frustrations are obvious, but totally this gives us tremendous pleasure and satisfaction. So with this, I want to acknowledge following institution, Nepal Agriculture Research Council, for providing this breeding materials, research stations in some cases, and expertise. We work in a very close collaboration and synergy. We are not competitors at all. So excellence in breeding for SNP genotyping and marker assessment. And Washington State University, K.S. Gill, he visited our field, and we have the germplasm from his program as well. And Chengdu Institute of Biology, also we have Chinese material with us, which are really amazing material, very high yielding and stripe cross restoration material. We have identified some lines that are near immune to stripe rust, but since you know, stripe rust is not a disease in the Tarai region, we are not much we cannot work much on stripe rust. But in the future, this Chengdu material will be very useful for our national wheat breeding program. So finally, thank you for your attention. Thank you.
Thank you, Professor Dr. Madhav Prasad Pandey, sir.
Today, I would like to proceed with today's session. On the very first session, we do have a keynote speech. And before the speech, I would like to introduce Dr. Prabhat Khanal. So, having the Masters in Agriculture from Robert H. Smith, Faculty of Agriculture, Food and Environment at the Hebrew University of Jerusalem, Israel, he has completed his PhD in Nutrition and Physiology from the Faculty of Health and Medical Sciences, Department of Veterinary and Animal Science, University of Copenhagen, Denmark. And currently he is serving as the Associate Professor of Sustainable Animal Nutrition at the Faculty of Bioscience and Aquaculture at the Nord University, Norway. So it's a privilege to have him here as a keynote speaker. And I would like to request Dr. Prabhat Khanal to be on the stage for his keynote presentation. Thank you very much.
So I'm really happy that I could manage to be here this morning. We just had breakfast, so I think it would be a great topic to talk about a little bit food system, and my background is animal nutrition, so then I would be mainly focusing on animal food production this morning. And we are talking about the alternative feed and food sources. I will also give you a couple of examples. AFU students, PhD and master students, they have involved in different research in Norway, but I will also discuss a little bit about that today. We have issues with the slide, but while it is fixed. So I did my bachelor's in agriculture here, and I passed out in 2006, just to give some perspective. It's working. So when we talk about the food, we should really talk about the populations. We all are familiar with this topic. Population is growing, although the population rate, annual growth is decreasing, but the total population is increasing. So what does and there are a number of reasons, of course, why growth rate is going down. There are the policy issues, some biological factors, so also the aging population. There are a number of factors, but what we are concerned is we have many more mouths to feed in the future. That means we need to supply more calorie, more protein, and there is a feed and food competition. For example, if you have a soybean, you give soybean to poultry, or you give soybean to kids, or your human population, for example. There is an issue, and we are familiar with the climate change and impact on agriculture. And particularly in the developing countries, we are already, there is a gap. Animal product consumption is low. With the socioeconomic changes, it's going to be high. So there is a demand for animal product. So that means we need to find a way how we can produce and consume animal products in a sustainable way. Yeah, we had a breakfast. I don't know how many of us had. You drink more than 300 ml milk per day. That is what AFU says. If you are 18 or above, then we are supposed to drink 320 ml milk per day per capita from the developing countries. And then I try to feed this data to what was the production in Nepal. So a couple of years ago, we mapped it, and we found that there is a huge gap, how much we produce milk and how many mouths that we need to feed through milk, for example. You can look in the upper line, there is a demand, and then it's down, there's the daily milk production. And we went further and tried to find what happens in the future. And then there is, due to the population rise, then there is even higher demand for milk. And production, I don't know how much we can capture that, and how, through nutrition, through breed, and that's also a very, very difficult scenario. And if you look at the meat, that is also a bit scary situation here. In the developing countries, we consume 27.9 kg meat per person, annual consumption. And in worldwide, you have a bit higher, and developed country, we have like 80 kilo of meat, per person per year. So that is the situation that we have. Then I also took the population data and tried to fit this. And we took the ministry data and found out that the production is really down, demand is really up, and we try to go even further and look into the different average. Okay, if Nepal, if we consume based on the developing country average, how much we have to produce, and based on the developed country average, where should we go? And if you look at these three lines, so there is a huge gap between how much we are producing, we can produce, versus how much we need to really, what's the demand there? So that tells us that there is a challenge to animal production, and especially nutrition is very important. As we know that if in a typical animal farming system, 60% of the cost that actually goes to feed for nutrition. And we don't really have an area to grow more feed resources. That means we need to really find the novel feed resources, something alternative, something less competitive between human and animals. So that is urgent. That is what we need to find. And then we set up this project, a collaborative project between Nord University, Norway, and two universities in Nepal, Agriculture and Forestry University and Kathmandu University. And this is the first NURPAT project of AFU here. And we focus on a couple of, or more than 4 different key things when it comes to research. First is the insect as a novel source of protein, aquatic plants, and also the forest biomass or byproduct. How we can utilize this to generate the alternative protein. And one key point is missing here, that is the capacity. These are the resources, but we need to develop the capacity. Students we need to involve so that they can drive the research through their PhD or master thesis, for example. What's the progress now? We started in 2022. We have a full degree master student, 6 from AFU or a couple of from the other university, but mainly organized through AFU. They started 2 and 4 in different years, and semester exchange program, that is for 6 months. Out of 16, 8 completed. Then PhD student 5 and 2 PhD students from AFU, they visited, or 1 returned and another is still continuing there. And we have also the course. We also need to develop suitable curriculums in this field. So we have started the course also, the course development, 1 at KU and 2 at AFU, for example. And through this project, we developed established the black feather fly lab at AFU. We were really nervous at the beginning that how we could do that. There were a number of different parameters, and our PhD students really work hard to establish this. Going to how we get the larva in. Then we go to mating, and then how we can generate the larvae through egg collections and then further processing. So we started this. And Bola Gautam, he took the 13 different bio-waste just nearby this area, from also the Naranghat and also from here, and look into the different bio-waste and feeding to 5-day-old larva, then maintain the colony and looking into number of different profiles. Try to find out if we are going to commercialize this in Nepal, what sort of bioresource is important. We looked into that. This paper is about to come out. Maybe this week it will be online. You can also check more about this. But this is to the best of our knowledge, first study from Nepal really looking into the feeding trials in BSF. And what we saw, we looked through the growth, and usually the paper used to say the growth is linear, but we found the non-linear sort of logistic growth curve. We immediately found that, okay, it peaks somewhere in the early stage, and sort of it stabilizes the growth. We saw this kind of nice graph here, and we look into the rapeseed cake supplementations, and that was never done in BSF flies before. We took the bio-waste, and we also looked into the rapeseed cake, and then try to look into the profile of different feed materials here. You can in the right side see the number of different bio-waste that actually we use. And if you look in the upper line there, in the vegetable waste, for some reason they really like the vegetable waste. The growth is really high. You can also see, and if you do the supplement the rapeseed cake, and it also somehow affects the growth. But we use only rapeseed cake. You can come here and look in the yellow line here. We couldn't really, they couldn't really survive on that. We thought they had a high protein rapeseed cake, but it was ammonia concentration was high, some of the other toxic materials, so they couldn't really survive. But the rapeseed cake appears to be a very good supplement on the bio-waste based on our data. And we could look in the survival, where the bioresources rich in soluble carbohydrate, they really promote the growth. But on the survival, if you look in the survival, larval survival, the protein-rich diet plays an important role. Then you can think about it, okay, if you are going to harvest the larva for other consumption or use for animal feed, then you just feed the bioresources that is rich in soluble carbohydrate. If you are going to maintain the black soldier fly for reproduction, okay, I will collect the egg, it will go to the pupa and larva and adult and so on, then we need to really move towards the protein-rich diet. So, because the survival is high there. And crude protein content, there was no surprise that the larva that was fed the high protein-rich diet, they also had a high protein content. You can see about 45% protein on larva, but in most cases, if you see between 30%, but if you supplement the rapeseed cake, then the orange line or brown, then you can see that it increases the protein content. So we found that in vegetable waste plus rapeseed cake appears to be a best substrate for black soldier fly in Nepal, at least from these localities. And we look at the crude fat, and for the crude fat, and then if you give the carbohydrate-rich diet, then they can really formulate the fat. This is mainly through the endogenous fat accumulation. They can synthesize the fat if you give the soluble carbohydrates. So that means the soluble carbohydrate to protein concentration of, let's say, 2.5 to 1 or 3 to 1 appears to be a best combination for black soldier fly, both from the growth and also the nutritional value perspective. And then in Norway, we established the yellow mealworm production facility. The yellow mealworm is a bit different than black soldier fly in a sense that it requires a bit longer time to complete the life cycle. But it is authorized as a both food and feed source in European regions. So it is a human food in addition to animal feed, for example. And what I'm doing here with the involvement of students from AFU and KU, we study themselves first. We try to look into their growth. We try to look into their nutritional values. We plan to extend this to the welfare and breeding as well, and also the gut microbiome. I look into the gut microbiome in other production animals, but I was curious what happens to the gut of yellow mealworm larva. And it appears to be a typical monogastric digestive tract if you look at this. And then we also found the number of different bacteria there. And if you look at the protein content, it is more than 40%, and fat more than 30%. It is really the mealworm. It is really the superfood. 40% protein, 30% fat, and even in a fat, 75% is unsaturated fatty acid, healthy fat. And I have just submitted the paper. It will come out soon, and I'm comparing these to like avocado, for example. Is it a superfood like avocado with the protein-rich avocado, for example? So this is really an interesting candidate insect. And if you look on the right side, this is EAI. This is the essential amino acid index. What does it tell? It tells based on how many amino acids required and how many amino acids that the feed item contains. If it is a 1, that means the feed completes all, supplies full amino acids required for your body. But here, if you look at it, for the yellow mealworm larva, it is 1.65, way better than soybean meal, for example. In terms of amino acid profile, this is superior to soybean meal. If you just take an example of growing piglet, of course, essential amino acid index is species specific. We need to target the species, of course. A number of master students from AFU, they are also involved in this. And I was mentioning the gut microbiome. When we profile this, we found mainly the firmicutes and proteobacteria. They are really dominant phylum inside the gut of yellow mealworm larva. And they adapt very well in response to different feed items and also immediate nutritional challenges. What I did here is I just fasted them for 24 hours and look into the gut microbiome profile. If you look at on the right side the picture, during fasted conditions, proteobacteria, they are mainly involved in nitrogen recycling. They are really going up, relative abundance. But if you look at on the fed conditions, the population of firmicutes, the bacteria, that appears to be high. And that makes a lot of sense because they are mainly driver for nutrient utilization, mainly the carbohydrate or fiber fermentation, for example. Then I talked to Vola while we had a meeting, and many people are doing on research on a black soldier fly, and many people are there doing their research on yellow mealworm. But in Nepal, it's a fantastic place with the landscape, and then if you look at the climate, it is a fantastic place to profile the number of different insect species. And we talked, and then we set up this project. Let's try to collect as many insect species as possible from Nepal and try to profile the nutritional values. Let's do that. And then based on the time and so on, he could collect the 30 different insect species from Nepal. And we looked into nutritional profiling. We have just started. We have the data about to come. He also took the other arthropods apart from the insect, in addition, but they were mainly 30 different insect species. If you look at the Orthoptera, and it has a quite high protein content compared to insect from other orders, for example. Why is that? Why grasshoppers are so good in terms of protein? We are trying to understand now. We are looking into that. Why does it happen? Why there is a species differences? Is it due to the feed? Is it due to the environment? Is it due to genetics? Or there is an interaction? We don't know. We are just looking into this. And some of the other insect species and Coleoptera, water beetle, for example, this also appears to be very high protein content. But why only that within this Coleoptera? We are trying to understand this more. But data appears to come and they look promising, especially Orthoptera, but the other insect species as well. Then the next part is we have one PhD student. He just finished a feeding trial using yellow mealworm diet in layers. For some reasons, I'm interested in layers. Broiler is a big industry, but there is a very few publication on layers because it is difficult to do based on the time, cost, and so on. We could manage to do this. Last week, we euthanized 96 animals from there. I could do that before coming here. And we look into animal growth and production, look into different egg quality parameters. What was the experimental setup? Experimental setup, we started with the control diet, 25% replacement, soybean replacement with yellow mealworm larva, and 50% soybean meal with the yellow mealworm larva. And there were 8 replicates, and we keep the 4 balls, and then we try to follow them through whole laying period. Let's say from week 18 to week 28, for example. So we try to capture the peak laying period. That was most important. We haven't really looked into data yet, but I just found, I was just checking the OneDrive, and I found that he had this graph. So I thought I would just put it here. In terms of weight, it is promising, and then I was also following them, the layers. They really like the insect-based meal. It makes a lot of sense. In the nature, they do that. And then our layer chickens, they were really domesticated through wild balls. And they are used to its insect, not in the cage system or not in indoor feeding, for example. That also shows here growth is interesting. And also the feed intake is also it is really good in insect-based feed. And you can see that maybe from week 21, you can see that why the weight was going up and then why it is going down. So what happened there is that we learned that we keep the 4 birds in the cage, and then once the laying period is started, and then they start to pick each other. Cannibalism occurs in the 4 birds. We thought that it would go okay, but it didn't. Then we had to really turn the light on, and when you turn down the light, it also affects the feed intake and also the egg production. That is what we see on the graph. If you are wondering about why there is not a straight line on there. Then I will focus on another interesting part, that is the nutritional value of freshwater aquatic plants. Then sometimes when we are thinking about doing master thesis and PhD thesis, we try to look for the thesis. Where do we look for the thesis? In Google or through ChatGPT or DeepSeek or whatever? We were sitting together, and then we just walk around the AFU and in the fishery lab and so on. We found these beautiful freshwater plants not utilized. And they are considered the weeds, for example, invasive plants even. So then we try to look into what would be the nutritional values of those. Are they just weed or they have some nutrient? And the master student from aquaculture or fishery, he collected different samples of 3 important freshwater halophytes or plants here. Aeroleaf pondweed, it is there. And the lotus and water lettuce. He collected from here and he took the samples in Norway and then he analyzed there. And what we can see is that, no, they are not really weed. They contain 20% protein, almost like a protein source. Even, mainly in the hastata, but in other species as well. But is it interesting? Can we utilize in some way? Because the plants and fish sort of live together. Everything what we learn through the nature, they live together. Maybe it can be used as a diet for fish. So I think he completed one trial in fish using these fresh water plants, making the feed himself, and here at the lab, he completed that. And we are looking into the data further. Are they all? Just the insect or freshwater plants, or what else we can think about when you are thinking about the alternative nutrient source? Snail, that we have work. On earthworm, I had one trial in Norway, and single cell protein. The one student, master student through this project, she completed thesis on that, purple non-sulfur bacteria using wastewater. An aquatic plant, as I mentioned. What else we could do? But the list is it is growing and growing and growing. We really need to find what is available nearby and what is possible and what is feasible. I was talking about lots of fancy things and so on when it comes to alternative feed resources. But we have to be realistic. What is the reality point here? Number one, economically viable. Can farmers, if they want to become an insect producer, can they survive economically? Is it profitable? With this profit and then income, can they support their family and kids and so on? We need to look into that. There are number one is for insect, we are using bio-wastes. That is of course the surplus biomass. But how can we scale up? How can we increase the production per day in terms of tons, not in terms of kilos, for example? That is critical. And environmentally sustainable. We always need to take the environment into account. Doesn't matter while producing insect or while using insect as a feed, and what happens to the animal production system there. Can insect reduce the methane production from cattle or ammonia production or from pigs, for example, or poultry? We need to be mindful and we need to look that part as well. Not only being excited about the nutritional values of insects, for example. And socially acceptable. Sometimes we forget that. We only focus on core science and p-values and interesting data and so on. But consumers should perceive positively. They should accept it. They should be willing to consume this, either as a feed for their animals, or if you are talking about the food, also how many of us really are interested in consuming insect or freshwater plants, for example. We need to look into that part as well. Then all the data I showed, it came through number of collaborations, through AFU, KU, but also the number of different universities in Europe. So I'm really fortunate and I'm grateful to have that collaboration and then support to go through all this different projects that we could support the student. That's the most important thing. We want to support the student through the project so that they can excel on their research. We are just promoting young generations to take this field further. Thank you for listening.